Good afternoon, everybody. Thank you for coming. So yeah, it's my really great honor today to welcome Professor Ruoff from America and from University of Texas originally, and now he's over in Korea in Ulsan. He's extremely famous in the field of carbon, and especially in graphene. Yeah, it's really a big honor to have someone so distinguished to come over to I2CNER and to show around the labs. So yeah, I met Rod not so long ago in Jeju in Korea in the Carbon Conference, and he was giving the plenary talk there, and it was very impressive, and I thought it'd be really nice to bring him along today to share kind of all of his work with you guys, and hopefully we can spark up some collaborations and yeah, maybe continue some work. It's very close, just over the water to where he is now, so we can. If you have some nice ideas, then maybe we can set things up. Okay, so without further ado, I think I'd like to welcome Rod to the stage, and yeah, please go ahead.
It's a great pleasure to be here. Indeed, it's a 35-minute flight from Busan, so it took longer in the taxi to get to the airport than it did in the airplane, which was great. So I'd like to spend a few minutes telling about our new center and explaining where that came from in Korea and what's going on, and then delve into some research that we've actually already published even some years ago. So our center is so new, it'll be a few more months before we start to generate publications. So this is a picture actually from about 5 months ago, and I'll just mention a few people in here. Of course, the important people are the students and the postdocs, but and we've grown quite a bit since then. But Professor Belowski is a very talented synthetic chemist. So Chris Belowski is our first group leader, and then we have affiliate faculty such as their faculty at UNIST, but they play a role in center research, like Jung-Hoon Lee, who runs an aberration-corrected Titan TEM, and other colleagues who are also external or affiliate faculty in our center. Just to show any synthetic chemists, this is a bit dated because now there would be people working here, but the labs are very good in terms of our 3rd and 4th floor capabilities. So we have 32 8-foot chemical hoods, and the 6-foot hoods in the back are where the rotovapes are. So these are configured now with Schlenk tube lines, so they're fully equipped for, if you will, hardcore synthetic chemists to be able to do wet chemistry with. Then we also have a separate room where we have our dry boxes or glove boxes and solvent purification systems, so that is also very well set up for air-sensitive chemistry. On the 2nd floor, what I call it the dry lab, we have now probably about 30 different CBD systems. They're not all within the center. Part of that floor is Professor Hyun-Suk Shin, but we collaborate closely. And so we're very interested also in systems that might be home-built and quite innovative, different than conventional approaches to making materials. Some of them are not CBD per se. There might be other sorts of approaches. For example, at lunch we were talking, we're going to be getting some very high temperature furnaces in that go up into maybe 3,400 Celsius, and doing things that I haven't done before in my career. So let me now take a moment to tell you, well, what is this center and what is this institute? The Institute of Basic Science is a new concept in Korea, and it's meant to, in some sense, be like the Max Planck Institutes in Germany. In fact, this is a brainchild of German physicists who were Max Planck Institute directors and then became emeritus directors, in a sense, talking with Korean colleagues, and that discussion led to finally this institute being formed, which is located in Daejeon, or Science City in Korea. So the institute ultimately will be an umbrella organization for about 50 centers, of which ours is one. Currently there are 25 of these centers that have been established in Korea. They're in universities like UNIST, or in some cases, particularly in the future as new buildings are built, roughly 15 to perhaps 20 will be in Daejeon itself as standalone centers, not on a university campus. And those will be probably having surgeon grad students at KAIST to do the research there and postdocs. And so the Institute for Basic Science is funded at $5 billion US, and these will last for 10 years and then possibly longer if the whole program is successful. So with 50 centers, roughly the average funding per center is around $100 million, but there can be smaller centers, and some of them can be bigger. And so 25 more will still be founded in the future, and they range from, we now have 7 or 8 that are chemistry oriented, to physics of different types, including high energy physics, very short time pulse laser physics, biology, medical sciences, and mathematics. The idea also is to do very fundamental work. And so this is a bit of a departure for Korea. Of course, there's a lot of talented Koreans who are doing fundamental work and have been doing it for a long time, but the idea here is to really embed in Korean culture this Max Planck Institute-like system, so that fundamental research can be fostered for many decades into the future, but the funding is for 10 years currently. UNIST is a new university in Korea. We're now entering our 6th year. We're in the same system as KAIST. If some of you are familiar with KAIST, Korean Advanced Institute of Science and Technology in Daejeon, and GIST in Gwangju, and EGIST in Daegu, and POSTEC is typically considered a part of that as well in Pohang. And so our campus is located outside the city of Ulsan. We're in Ulsan proper, and we have a very scenic setting with some beautiful hills, or let's say small mountains surrounding us. And very conveniently, we're about a 5-minute taxi ride from the high-speed train Ulsan connection called KTX system. So the Ulsan KTX station is very close to UNIST. And we're currently in our 2nd phase of building, so they're building out these additional research facilities here. So if you were to come and visit us, you would see construction underway here, and these buildings are all in place. And our building happens to be right here, Building 101, where most of the center facilities are. And we have some interesting other facilities. We're particularly good at electrical energy storage, so I think that resonates with your center, your institute, excuse me, here. Jae-Phil Cho, for example, leads a significant group of faculty who are among the best in secondary battery, particularly lithium-ion battery research. We have a stem cell center, now called the Hans Schürler Stem Cell Center. He was visiting UNIST frequently, and then he won the Nobel Prize. And that is actually a Max Planck Institute UNIST collaboration that might develop into a sort of a foreign Max Planck Center for a 10-year period. So those are a couple of interesting aspects of our campus, in addition to significant materials research that our centers are involved in. Do any of you have any questions at this point about IBS or what these centers are? Okay. So this was a picture I took out of the guest housing where I was with my family for a few months, and it shows the fog rolling down one of the valleys. So it's quite a nice area. And then of course, I should show a picture of Korea to show that we're along the coast. Ulsan is a major port. Ulsan is also an industrial center of Korea. So not semicon industry, which is up in Seoul area, but for many other things, such as chemicals, petrochemicals, energy, car factory, the largest auto works in the world is Hyundai Motors, and then also the Hyundai Heavy Industry Shipyard. And so there was a sense that what was missing here was a world-class university, and so there was a push to establish UNIST and to have it be in the same system as KAIST. And future goals involve things like building something like a Silicon Valley, a high-tech aspect to the heavy industry in this area. And so those are part of the reasons why UNIST came into being. So let me now switch to talking about some of the goals of our center. I'll be somewhat brief because we have a lot of talented people, and the charter is very simple in a sense. We want to be an engine of creation of new materials. So our focus is really on new materials. And then once make those new materials primarily from carbon, but related materials like boron nitride and or others. We can't canvas the whole periodic table, or it wouldn't really be a center with any focus, but the objective really is to make new materials, understand their structure, understand fundamental aspects such as kinetics, thermodynamics, pathways for chemical reactions, bonding configurations might be unusual, and so on. And then to study physical and chemical properties, perhaps in some cases also biological properties. In terms of possibilities for applications, we hope that our materials in certain cases will have a big impact, but keeping with our charter in terms of fundamental research, we would then look to collaborate closely with other groups. So some of you might be aware I've done some work in supercapacitors and a little bit of work in lithium-ion battery research and so on, but we won't really focus on those things unless it's a very fundamental issue, like what is the distribution, the spatial distribution of ions at the electrode surface, and the fundamental aspects of the double layer is one example. That might be something you might go into. And so I'm showing you here some examples of work that we would do. We will make model compounds, so not only highly extended materials, but actual chemical compounds, but we'll also focus on trying to make extended structures, 3D structures, two-dimensional structures that I'll come to in a little bit, such as the so-called negative curvature carbons, or minimal surface structures, or also referred to as Schwarzites is one example. I'll come back to that a little bit later too. So the approaches here are very influenced by wet chemical approaches primarily. Another example can be trying to make new types of 2D materials, such as with extensive sp3 carbon bonding. So you might think of it as an ultra-thin layer of diamond. It's not diamond per se, and I'll come back to that as well. So various ways of achieving control of the bonding of carbon. So very fine control of the spatial distribution of sp2 and sp3 carbon is one example. Our goals of the center. And I just wanted to mention, we have these other centers. Steve Granick, your very close connection with Illinois Urbana. Well, he's a famous faculty member previously of University of Illinois at Urbana, and he is the director of this center. His background is polymer physics, among other things. And KJ Myung was lab director of an NIH facility in the United States. Strong background in studies of genomic integrity. So these centers, these federal centers, in this case, it's perhaps something like your relationship here with Kyushu University. Our students are UNIST students. Graduate students get a PhD from UNIST. They might also do a certificate or something from our center. And the postdocs are, however, not affiliated formally with UNIST, but they use UNIST facilities, and there's a sort of a friendly exchange in that sense, the relationship between this federally funded center, which is on the university campus. So now let me come to graphene, and I want to briefly give you a history of graphene and talk a little bit about some of the research that we've done, and then I'll come back to talking about, I'm going to destroy your stage here if I keep stepping out. I'll come back to talking about some of these things we'd like to do in the future that I briefly mentioned, that like these ultra-thin sp3 bonded films. So many of you might be aware, but a few years ago most people weren't, that there actually was a definition of graphene, and it goes back a bit to 95. It actually goes back to an article published in Carbon in 1986. Hans-Peter Bohm and about 50 other authors. It looks like one of those high-energy physics articles, but it was about terminology and the introduction of the term graphene. It's interesting where it comes from, given how much chemistry is now involved, but the term was, in a sense, invented because of the needs of physicists who were studying graphite intercalation compounds like Millie Dresselhaus, Stuart Soll, and many people here in Japan and elsewhere. As they intercalated graphite and the layers were pushed further apart, in terms of a physical system, it began to be necessary to have a term in which one could talk about the physics of the individual layers. And so this was, for the International Union of Pure and Applied Chemistry, embodied in this sort of language. I also like to show this this IUPAC nomenclature because graphene means different things to different people. And so if I talk to a polymer physicist, they view graphene typically as a very fascinating macromolecule. If you talk to a theoretical physicist who's studying transport properties and so on, graphene has a linear dispersion and a direct one. And so my friend and colleague Toshiaki Inoki at Tokyo Institute of Technology, now he's emeritus in physics, he very emphatically said to me over beer, you know, Rod, monolayer graphene on nickel 111 is not graphene. I said, well, why is that, Toshiaki? He said, well, because it's so strongly chemisorbed that it doesn't have a linear dispersion or a direct point. So I said, so if I put benzene molecule on nickel 111 and it dramatically alters the electronic spectrum or perturbs it, is it no longer benzene? And so we had kind of a fun dialogue, but I should respect his perspective on what graphene is. To me, it's still graphene, it just happens to be chemisorbed. But for this definition, it isn't, because this material can never really be found and studied, probably because it's sitting in a vacuum, not touching any surface, no interface, with no defects and no impurity atoms, etc. And so there's also a fascinating aspect about the discovery of graphene in that one can make a case, as I do here, because someone had to have discovered the material experimentally. As you may know, a Canadian physicist discussed this material in terms of this linear dispersion and direct point and published in 1946. So that was quite a bit earlier. But the funny thing about this story is that a theoretician made the experimental discovery of graphene, and I'll tell you about this in a moment. But if you want a deeper discussion of this, I give a history that does delve into that in this Perspectives that was published in the MRS Bulletin. And it's an interesting, I don't actually have maybe I'm going to come to it in a little bit, so I'll just tell you the story. Gabor Samarjai, one of the world's best surface scientists at UC Berkeley, where he's been for his whole career, was one of the inventors of modern surface science. So the ultra-high vacuum techniques that were needed for doing surface science were invented in the 1960s. And then the very first problem that he chose to study was the consequence of speaking with people in industry. And the people in industry were explaining that very small metal particles that were dispersed on catalyst beds were being poisoned as they were exposed to acetylene and ethylene and other hydrocarbons. And so, as you know, in the petrochemical industry, almost everything is tied around catalyst beds and cracking, the oil and then ending up with important chemicals. And so Samarjai, the first experiments that his group undertook were to take single crystal palladium or single crystal platinum and use that single crystal as a substrate and heat it to about 700 degrees C, and then essentially impinge acetylene or ethylene on the surface and use low energy electron diffraction, LEED, to look at the surface in a sense, to interrogate what was happening on the surface. So they had palladium-111, for example, and they saw the LEED spectrum change as a function of the dosing with acetylene. But they didn't assign the LEED patterns. They published 4 papers in different journals where they didn't actually state what they had, which is fine. That's good science. It moved the field forward. And John May was one of the world's experts on LEED, a theoretician, and he read their literature and published a short article in Surface Science explaining this is monolayer graphite. And then some of the LEED patterns were actually multi-layer graphene, we would call it now, that were either in the Bernal AB stack configuration or misoriented. So it's quite fascinating, sort of back to the future story, because now, we and the worldwide community would love to have very fine control over the degree of misorientation between the layers, because the symmetry influences certainly the physics and perhaps the chemistry in interesting ways. In fact, I'm quite sure it will influence interlayer chemistry, obviously, if you change the interlayer registration between the atoms. So, why are we interested in graphene? I just list out some of the reasons here. It is often said in the popular press that graphene is the strongest material that could exist, so I just want to show you that that isn't true. If we talk about defect-free materials, diamond along the 100 direction will be stronger, all things being equal. So it's often also mistakenly said or discussed that strength is something like a thermodynamic parameter, but it isn't. It's a kinetic parameter. So you should think about these numbers in that context, because it depends on how the load is applied. So if you apply a very small load to a perfect carbon nanotube, which would have a strength nominally around this for some type of discussion of the loading that we would do, and you wait forever, it might break. So what is the strength then? So there's a kinetic aspect to strength, but in a sort of a fair comparison, apples to apples, then diamond along this direction is much stronger. But does it really make any difference? What are the strongest materials that we have now? The strongest material that we use is highly graphitized carbon fibers, such as made by Toray in Japan and Cytec in the United States, and they end up in the Boeing Dreamliner and in other applications. That's about 7 GPa. So 7 GPa is somewhere over here, and 130 is over here. We have an enormous range for exciting possibilities for strength. And the stiffness is almost a given, I think, because the defect density would have to be extraordinarily high to alter the stiffness very much. It's also the case that people can confuse stiffness and strength. Those are different things. And so, if you're not missing too many atoms, your stiffness with graphene and with carbon nanotubes is going to be close to that number. Is glass a strong material? Remarkably, if you take the trouble, as some experimentalists have, to prepare fiber optic with very few surface flaws through careful polishing techniques, and then you make a measurement of the strength of glass at liquid helium temperatures or liquid nitrogen, so there's absolutely no water present, even though it has a modulus of only 80, silica, for example. It has a strength of 22 GPa. So you might ponder the implications of that in terms of my talk. If you have questions, I'd be happy to talk about that, because I think there's some exciting directions for research there. So in terms of having very low density, being an atom layer thick, you also have a very high surface area. And that's very interesting, including potentially for electrical energy storage, but it's sort of just obvious that if you have an atom-thick material and it has a low density, it's going to have a very high specific surface area, but also everything is an interface when you're working with these sorts of 2D materials. There's been a very interesting paper published recently from the University of Manchester from Andre Dimes' group. So defect-free graphene has been shown to be impermeable to helium, but it's now known that it's not impermeable to protons going through, and even more so through hexagonal boron nitride. So that was a very interesting result. But it is nonetheless a very interesting barrier material, and I'll show you one example where monolayer graphene can protect a neat metal surface from oxidation, for example. So it might end up being very important for corrosion. One can write down a long list of applications. This slide is probably 4 or 5 years old now, so you might have additions to the list, and maybe some of these should be falling off the list. But there's, I think, a tremendous excitement about these 2D materials now for good reason in terms of applications, even though our focus may be fundamental research now particularly. There's a lot of exciting possibilities here, including some of the work at your institute. Okay, I'm sorry, this slide was out of order, so I'll simply let you read this, and you can see this background, sort of ironic aspect of a theoretician making the discovery of graphene. These are the papers by Summer Jai that I mentioned, beautiful papers. Why didn't the industrial researchers understand what was happening? That the small nickel and palladium and other particles were being coated by something like a fullerene shell, because they didn't have the sorts of experimental techniques we have now. They might have guessed that, but they didn't really have a way of discerning a monolayer of sp2 bonded carbon completely coating the metal particle to completely poison the catalysis. And then there's also a really interesting background to the so-called Scotch tape method, or this method of using tape to make very thin samples. It actually extends back to the 1950s, but there's some lore that I think wasn't published, and so I'm still collecting the history on this. But Bob Frint, who's now an emeritus professor in Canada, had shown that it was possible, although Scotch tape didn't exist because it's a trademark term from 3M, cellophane tape did, so they used cellophane tape, and they got individual layers of, for example, niobium diselenide, and showed they were superconducting and so on. He got by himself, and then in collaboration with others. So it particularly has been useful with graphite itself for making ultra-thin support films for TEM. So the breakthrough at Manchester was to find the route to getting monolayer insulating substrates, which was very important. But there is this sort of fascinating history, including making probably down to maybe 5 or 6 layers thick, but being a transmission electron microscopist and not a solid-state physicist, and that's a fantastic support film for TEM studies. So I began thinking about graphene actually shortly after Ijima's papers on the first multiple carbon nanotubes, and then back-to-back papers with the IBM Almaden group, Don Bethune's team, on the single-wall carbon nanotubes in '93. You know, make all the sense in the world to get this individual layer of graphite. But as I delved into the chemical literature, I was a little surprised, and then I realized, well, then it would have already been published, so it wasn't surprising that there wasn't a published method of exfoliating graphite into individual layers. So that's in strong contrast to clays of certain types and vermiculites, where you take basic water and some mechanical agitation, you can get mostly single layer material, such as vermiculite. And so what is it about graphite? And that's actually an active area of study. How could we take graphite, which is, I'm still US based, so dollars per kilogram, and exfoliate it very efficiently for all sorts of interesting reasons. Great progress is being made around the world, but we still don't have a method where we can get mostly monolayer and have it be scalable and so on. And so what we did in one experimental approach was to make pillars of graphite. And so we used highly oriented pyrolytic graphite, and I'm just showing you one pillar, an SEM image. My goal here was, if we knew the grain size of the HOPG, to create little pieces of HOPG that were smaller than the grain size. And so the grain size of this HOPG was roughly around 8 microns. And so we would cleave the HOPG, and then we'd spin coat a thick layer of photoresist, pattern the photoresist, put down a mask like silicon or aluminum, and then oxygen plasma etch at the end step. And that's a perfect mask stop because it makes the oxide. And so it would remove the surrounding carbon. And then we spent about a year with Michael Lerner's group at Oregon State University, because he had been making graphite intercalation compounds with perfluoroalkyl cations and lifting the layers apart to about 1 to 1.5 nanometers, extraordinary. And so it seemed to me that if we could do that with these sorts of pillars, then we'd probably get individual layers. And it never worked. It was quite remarkable. If you take graphite, it works beautifully. But if you take these pillars, it doesn't. So actually, one thing I want to do in the CMCM is revisit this and try to figure out why it didn't work. I think there's at least a possibility that the individual layers at the edge are somehow, from the processing, perhaps there's an ether-like linkage with the oxygen, they're somehow bound together, and they're not allowing the intercalants to go in. But we didn't really pursue that, and frankly, we weren't really funded to do this research, so I had to sort of stop it at a certain point, and then I moved from Washington University's Department of Physics to Northwestern University. But one thing we did do, and I'm proud of myself because I actually did this, because most of the time students and postdocs are doing everything. I rubbed the pillars very quickly with a silicon wafer, and then we looked with SEM, and they beautifully spread out in this manner, and you can see some are very thin, quasi-transparent in the center. We might call that multi-layer graphene now. We have to figure out exactly how thick it was. So another reason why this is probably worth revisiting is it gives you very well-controlled shapes, and then we could obviously pattern at all sorts of different length scales these days, including down to nanoscale. But there are fascinating issues associated with friction. And so if you have the A-B stacking between layers, then what you have is a relatively deep potential energy well in terms of how the layers are locking with each other. But if you misorient it off that A-B stacking, then it smooths out the potential energy surface dramatically. And you can have what may be super lubricity or almost frictionless sliding of one sheet with respect to another. So in fact, a colleague, Kunshui Zhang, who is in engineering physics at Tsinghua with his group, he's a theoretician, but they've done some interesting experimental work, have shown that if you use AFM and you try sliding certain layers in this structure, dislodging a little bit and then nudging them and so on, they slide almost with no friction for their work, and then in the AB configuration, it's very difficult to even move it. So Kunshui has become excited about the implications for manufacturing. So if you have questions about that, I'd be happy to delve into some fun discussions with him about that. So one thing we have done lately is sort of revisited what the scientists have been doing since the 60s. So there's a large body of work on monolayer graphite, just we would call it graphene now, but always sort of centimeter scale with single crystal and UHV, and very beautiful science. What we've done is we've taken conventional CVD systems and tried to find routes to producing large area graphene. And so one method that has been very productive has been copper foils. And that led us to invent some approaches that have also been very useful, I think very useful for the community. And so being somewhat inexperienced, we went way overkill here. We had an hour of exposure to hydrogen at temperature around 1,000 degrees C, 1040. In reality, we now know from our colleagues that probably 30 seconds is enough to remove the oxide layer on the copper, the native oxide layer, and then expose to a hydrocarbon like methane. So since our work was published, and quite appropriately, people have gotten away from methane in many studies. They've been looking at many other precursors, including halogenated precursors like hexabromobenzene that can form good graphene at 200 degrees C, and so on. I think all of that is incredibly important. Methane is the most stable hydrocarbon. That's why we need a very high temperature to get the growth to occur well on copper, as it turns out. So as we grow mostly monolayer graphene in our initial efforts on copper foil, so it's polycrystalline, it's not a single crystal. Recently there was an important finding in G1 Park's group at Cornell that if you buy a particular copper foil from a Japanese company, Naialco, and you heat treat that, you can convert the whole foil, which is about that long and about that wide, as far as where everyone looks, to copper 111. So I think this is an incredibly important breakthrough. So if you have questions about that, I'd be happy to discuss that too. But as we received our cold rolled copper foil, it turns out that when you heat treat that, you get mostly 100 orientation, which is not necessarily favorable for making really large, like whole foil on single crystals. Nonetheless, even with it having many different grain orientations as per electron backscatter diffraction, we got monolayer graphene over the whole foil. And then it could be transferred to other sorts of substrates. And so Qin-Kai Yu, when he was a research professor at University of Houston with growth of multilayer graphene on nickel, showed that if you supported it with a thin polymer layer, then you could dissolve away the underlying metal. So this sort of approach has been something that many groups around the world have used, but if you're not aware of it, I want you to please be aware that there's been a lot of progress on other sorts of transfer methods where you don't have to dissolve the metal, you can use it over and over, essentially ad infinitum, and dry transfer methods where you're left with less and less residue. And so for our center goals, this is incredibly important. We're putting some emphasis on trying to transfer graphene from its growth substrate so it has no residue. That's very challenging because if you just expose a sample to ambient, adventitious carbon or hydrocarbons adsorb on the surface. That's a very interesting thing, and it's another Back to the Future story. There were a couple of very nice papers published where I think the authors had accidentally missed some work done in the 1960s by a surface scientist. So if you ask the surface science community, is graphite hydrophobic or hydrophilic, they'll say it's hydrophilic. Everyone knows that. Actually, no one knows that. If you look up in the CRC handbook, it says it's hydrophobic. Most people think it's hydrophobic. I thought it was hydrophobic, but it's not. So if you take graphite and you cleave it, and then you immediately make a contact angle measurement, you get about 45 degrees. If you take graphite and cleave it, and you leave the freshly cleaved surface out in air for a few hours, you get a contact angle of about 85 to 90 degrees C. It's because of the adventitious carbon in the environment. Clean rooms are the worst, adsorbing on the surface and totally changing the surface energy. It's quite fascinating. In terms of some of the fundamental chemistry we want to do in our center, we don't want anything on graphene. It's quite challenging. Maybe it has to be done, therefore, with the graphene in the liquid. So it's constantly having these adsorbed hydrocarbons removed. So that's an interesting issue is, how do you do transfer of what you've grown? And are there other methods of growing graphene? I mean, this is frankly kind of tedious on metals. We're proud of our contribution. Companies have formed that are growing around very large copper foils and so on. But the kinetics are not anything like they are for making certain materials. I had an education from old Polaroid researchers who are among the world's leading experts in reel-to-reel or roll-to-roll processing. So Mylar is that coated plastic that has a very thin layer of aluminum on it. If you look inside plastic bags that contain potato chips, for example, they often have that silver coating. What is that? How is that made? Turns out the way it's made is a robot arm slams into a very large chamber, a huge roll of plastic, and chamber closes, the huge roots blower pumps it down to a few tens of millitorr, and then that's spun at about 60 miles an hour onto another reel, and aluminum is evaporated as fast as possible onto it. So why do I mention this? Well, growing graphene at the scale that's done now by companies that are making great progress with growing in copper foil will have an impact potentially on nanoelectronics in terms of transparent conductive films for flexible substrates and so on. Will it have an impact in building buildings like this with graphene? Or even using it in airplanes, or possibly cars and trains? No. It never will, because the kinetics is not favorable. The growth is much too slow. So we recently had a paper in Science where we achieved centimeter scale single crystal graphene. It took 12 hours to grow those in the copper. So I mention this because there might be talented young chemists who would know, or have some idea, how would you do this in a completely different way? Just think of the end material you're trying to make and forget about what's been done by other people. So maybe some polymer will be converted to graphene in the future, and we won't be doing it anymore on these sorts of metals. So one thing that was very interesting about our results on copper was that we shouldn't have gotten those results in terms of the thermodynamics. That is to say, the binary phase diagrams that have been published. So we found two papers in the literature, and we chose copper because we thought the solubility of carbon in it was at least very small, but not zero. So those two papers differed in their concentrations of carbon at equilibrium in copper at 1,000 degrees Celsius. But it's very small in either case. In one case, it's a few ppm. In the other case, it's hundreds of ppm. So we thought if we had a 25 micron thick commercial foil or alpha ASAR foil, maybe we'd get few layer graphene if it was a consequence of the carbon atoms dissolving down into the copper, and then when we cooled the copper, precipitating to the surface because the solubility at room temperature is really zero and you have a thin foil, so they don't have that far to diffuse. But irrespective of the thickness of the copper foil, we always got essentially monolayer. So we chose 25 micron thick and we got monolayer. It was surprising. So we tried 100, 200 monolayer. And so we felt pretty sure that it was a consequence of surface-mediated growth at 1040 degrees C and not a consequence of the cooling step. If you use nickel, where the concentration is 1 atomic percent, at 1,000 degrees C, then when you cool, if you have a thick foil and you've exposed for a long enough period of time that it's almost saturated, you get graphite on the surface, not graphene. But to really nail it down, we then took this approach of using C13 labeled methane and then normal methane during our so-called growth or exposure to methane. And on copper, we got an entirely different result than we did on nickel. And it's exemplified by these micro-Raman mapping images. So if you look at what you get here, you have regions that are pure C13 graphene, and then regions that are normal graphene, and then in the third minute, the islands stitched together, and the surface was coated, and so the catalytic activity stopped, and it stopped at a monolayer. If I were showing you the image from nickel, it would look like one uniform color because isotopic scrambling happens subsurface by diffusion, and what's on the surface when you take the sample out at room temperature is a consequence of precipitation. But in this case, this proved that in the first minute, nucleation had occurred, and then island growth, and then in the second minute, it grew further, and finally in the 3rd minute, it finished growth. So this isotopic labeling has been very useful for many, many different areas of our research. It gives you growth rates and so on, allows knowing where grain boundaries might be, and then you can interrogate them by a variety of methods and so on. And so the growth has been scaled. There are many more companies than this. I wanted to mention kind of an odd result we got, which was a consequence of Xusong Li and I being interested in whether carbon at least diffuses through the copper, because we couldn't see it being soluble in the copper the way the thermodynamicists had. And if you have questions about why the thermodynamics possibly is wrong, I want to be very careful. I'm not saying they're wrong. Then ask them later, and we can talk about that. And so what Xusong did was he folded over the copper foil. So here's the fold. And there's still some gaps here, and so the methane can get inside and the hydrogen can too, but the gaseous environment on the inside of this pocket is different than on the outside. What happens is on the outside, small grain size, multi-micron grain size graphene coats the outside surface in minutes, but on the inside it doesn't nucleate very fast. And the nucleation density is very small, so the nuclei are very far apart. And if you just wait long enough, those can grow into very large islands and very large single crystals. So this was a big breakthrough for us because we went from micron islands that merged, or coalesced, or stitched together to hundreds of microns, and then eventually to millimeters, and finally, as I told you recently, to centimeters. So that allows a host of new experiments to be done on large area single crystals. And one thing I was very interested in probing was the thermal conductivity of isotopically labeled graphene. So the thermal conductivity of isotopically labeled diamond has been studied fairly extensively. Interestingly, there were no studies of the thermal conductivity of isotopically labeled graphite. I think there will be in the future. That's starting. So by having large single crystals, it then became possible to look at the thermal conductivity of CVD graphene and know that you were dealing with a single crystal that spanned many holes. So Alex Balandin's group had shown that Raman, a non-contact measurement of thermal conductivity, could be done. They had used the Scotch tape exfoliated materials, so rather than an analytic solution as a consequence of a circular geometry, they solved by using finite element methods because they had a kind of irregularly shaped flake that was spanning a trench that they configured their Raman experiment on. So their very important work set us up to do these experiments with CVD graphene where we could have a simpler geometry, the so-called Corbino or circular geometry. And when you have that geometry, then you have, for the total thermal resistance, this expression. This can be determined by measurement. All of these parameters are geometric parameters, with the exception of the thickness that everyone agrees to use 3.4 angstroms for. And so with that thickness, then you can extract the thermal conductivity from this sort of measurement. Now, the way that's done is, I don't have a picture, but you first have to measure the shift, for example, in the 2D peak as a function of temperature. So you have a home-built cell where you put your graphene samples in, and then you change the temperature, and you look at the shift in either the G band or the 2D. Better to use the 2D because then you have a slightly smaller error because there's a bigger shift for a given temperature change than the G band. And so with these larger crystals, it's then trivial with the micro-Raman mapping method to know which isotopically labeled graphene you're dealing with. So as we're growing, we're controlling the flow controllers so that we're controlling whether we're putting in 99.99% C12 or a 50-50 mix or normal methane or inverse normal methane where it's mostly C13 but 0.8% C12. And then in our measurements, it's very important to measure the power absorbed by the graphene. And therefore, we're lucky that some of the membranes break. And so suppose we're looking at this one, and suppose it happens to be a 50-50 from our color coding, then we can slide this one underneath the Raman spectrometer, and there's no change in our instrument response function. Okay, there's no change in a minute in the power from the laser source, for example. So the data were quite interesting. The 99.99% C12 has a significantly higher thermal conductivity than normal graphene and inverse normal graphene, which quite interestingly lie right on top of each other, and the 50-50 is the lowest. And then as we go to higher and higher temperatures, it sort of looks like they converge. So if you have questions about this, I'd be happy to talk about this with you as well. Very interesting question about where is it going to max out as we go to lower temperature, and what could the maximum value be? And in 2000, David Tomanek's group published in Physical Review B a very nice DFT, well, actually local density approximation treatment of thermal transport in isotopically labeled ideal graphenes with no defects in terms of missing atoms. And they found that the maximum might be around 20,000. I have reason to think that might be the case because their predictions for right in this temperature range were very close to what we've experimentally obtained. So 20,000 is a huge challenge because you've got to have a little system that's going to work at those lower temperatures. So it may not be non-contact Raman, it might be these very clever microcalorimetric setups like Li Shi makes at UT Austin, where they've measured thermal conductivity of an individual single-wall carbon nanotube. But if it's so high, then we have to have really good single crystals that are quite large and defect-free. And then the amount of heat that's going to be lost because of the thermal conductivity being so remarkably high is going to be really, really low. And so Li Shi and I are trying to think of ways to do this, but it's an enormous challenge, but very exciting. So this is just showing we measured over a number of different samples. So I mentioned to you the possibility of graphene as a barrier coating, and there are some other interesting stories related to this. If you have questions, I'd be happy to tell those too. But we discovered, and then we didn't think too much of it until I gave a lecture at Cornell, that when you grow sub-monolayer, you have these islands that are separated from each other, and then you take the sample out and you do SEM, and we always found clearly the copper steps beneath the graphene in the SEM imaging, but between the islands we found very rough surface. And so it was obvious that the surface between the islands was being oxidized, and underneath the graphene it was being protected. Wow, it's interesting. Then I was giving a talk at Cornell, and some of the students got very excited by that, and Ji-Woong did as well, Ji-Woong Park. And they said, well, why don't we study that in terms of the possibility as a protective coating? And so we did. And we knew it was a protective coating, but then we undertook such a study where we actually tried to coat the whole surface of objects like a penny with graphene rather than submonolayer coating. And indeed, we found, I won't show you all the Raman and XPS data, that where the graphene is, the neat copper is protected, because remember, we removed the oxide in the first step where we expose the hydrogen before we grow graphene on it. But if not covered with graphene, the copper, of course, tarnishes when exposed to hot air, and our group focused on exposure to hydrogen peroxide, for example. And so we found that a monolayer would finally suffer by attack at grain boundaries, and then that would open up, and then, of course, the surface would no longer be protected. So this is extremely exciting for a number of reasons. I'll just tell you one, but there are many, many reasons why this is very exciting. One reason is that stainless steel is quite expensive, although as remarkable as it is, ordinary steels are much less expensive, but they have to be coated with zinc, a sacrificial anode material to protect them from corrosion. And eventually, of course, that disappears and they have to be recoated. And so if it were possible to make steel in large quantity, but have it behave like a stainless steel, at the cost of normal steels, that would be extraordinary. You might have questions about the role of graphene in galvanic cell and so on. So if you do, I'd be happy to talk about those things with you. Okay, coming back to what I told you before about sp3 bonded layers. Leonid Chernosatansky is a theoretician in Russia who came up with the idea of studying AB stacked bilayer graphene, but fully hydrogenating top and bottom surfaces in a density functional theory calculation. And I think kind of remarkably found that it drives conversion of the well-separated layers to have interlayer bond close to the bond distance in diamond, a little bit longer. And then other groups studied this as well, including with fluorination instead of hydrogenation. And, you know, that's interesting, and it's definitely worth pursuing in a variety of ways experimentally in terms of sort of the pristine material in large area. You know, we understand that you know, we're typically having our bilayer graphene. We'd like it to be AB stacked on metal substrates. That's where we start. And so we studied, in terms of DFT calculation led by No-Jung Park, what happens if it's on a metal surface. And this group found experimentally, in some sense, supporting evidence for our calculations. They also did calculations. And briefly, Noah had, No-Jung previously had studied diamond energetics. And so if you have an unterminated diamond surface, it's not terminated, for example, with hydrogen, it's a high energy surface. And so one way of stabilizing such a high energy surface is to have an epi-matched metal surface underneath, like nickel 111 or copper 111 as it turns out, or cobalt 0001. That's what we treated in our paper. The dangling orbitals on the metal atoms are perfectly lined up to satisfy the dangling sp3 orbitals on the carbon. And so that surface can also stabilize this transformation. And we also found from our calculations, so it's not really been proven yet experimentally, except for this initial result, I would say, that you don't need 100% hydrogenation or, say, fluorination. Around 30% seems to be enough. And also, you can do this on more than just bilayer, as long as it's AB stacked for graphene, up to about 7 or 8 layers. The energy, extra energy, free energy driving the transformation gets smaller and smaller and smaller. So inside the DFT calculation, when you get to about 9 layers, it doesn't convert by hydrogenation of the top surface. So what this group found, they grew mostly 4-layer graphene AB stacked on platinum by the platinum 111 single crystal by the precipitation method. So they're not saying that it's perfectly 4-layer everywhere, but by and large, it's 4-layer. And they found that when they deuterated the surface by cracking deuterium and exposing to a beam of deuterium atoms, per XPS, they got about 30% of the surface carbon atoms converted to CD bonding. And by XPS, they found about 75% of the original sp2 bonded carbon had converted to sp3. They haven't published any 10 images yet, and so there are lots of fascinating issues that I think you probably could think of. One of them being, what if you remove the metal? Does it pop back to being like graphite, or does it stay in that sp3 bonded form? So one thing our center is very interested in doing is pursuing this using graphenes, but as I mentioned earlier, also using other methods, maybe starting with monolayer graphene and building out chemically. Okay, let me now come to the negative curvature carbons. I'm a little long-winded here, so I'll be quick. Schwartz was a mathematician. He was a kind of a genius with minimal surfaces. If some of you are interested in soap bubbles and so on, and there's a lot of interesting aspects of minimal surfaces in polymer systems as well. But he published these sorts of pictures in the 1880s, and then Alan McKay, the crystallographer in England, who's also worked a lot on fullerenes, looked at this and said, well, of course, this looks like a carbon atom that's trivalently bonded, and so he called this negative curvature carbon. You know the total curvature on a minimal surface is 0, so what do I mean by that? What I mean is Gaussian curvature. Thus, at any point on this surface, if you take the two curvatures, they're always a saddle surface. The product of those two is -1, and that's Gaussian curvature. So that's why it's called negative curvature surface, but still a minimal surface. So, we've done things like take graphene monolayer chemically modified and mix into polymers, and then subsurface SEM imaging shows, yeah, it's highly wrinkled and crumpled. It's so thin, it's not surprising. Our thinking can be confused by seeing cartoons a lot. Just as carbon nanotubes are never, ever really perfectly cylindrical, though you may think they are, because we're always looking at those cartoons of them as such. You might think graphene's flat, but it's of course extraordinarily compliant, and so it always wrinkles and crumples. And so we happened to look at those were allowing percolation at very low loading levels, and we made these thin films and called them paper-like materials by exfoliating graphite oxide into individual graphene oxide layers and then reassembling them by filtration. And we see wrinkling in those sorts of materials as well. And so one thing we've done where I'll stop is just to start with graphite, and we spent about 1.5 years back around 2003 and 2004 trying to disassemble graphite, the very talented postdoc, and he didn't succeed, and so we decided we've got to make some progress in his research. So he went to graphite oxide, which has been around since the 1850s in terms of it having first been made by the British chemist Brodie, and it falls apart very nicely in water, and that's because of this extensive oxidation of the surface, so it's very hydrophilic at that point. In fact, the crystalline material, or the layered material which is formed through chemistry, is a swellable material that changes interlayer spacing based on relative humidity. So the amount of interlamellar water goes from a monolayer up to a few layers and then back to a monolayer as you change the relative humidity. So it falls apart in water. Of course, it's electrically isolating, not ion transport, but in terms of electron and hole transport. And it's also optically transparent. Its extinction coefficient is about 1/60th, roughly, of that of graphene. But then you can deoxygenate it to a degree with the whole list of different chemicals that have now been published on and get back to something akin to graphene, but still partially modified. And then that material can be very useful because it is electrically conductive. And so one thing we did, and I'll finish here, is we took graphite oxide. So we didn't put it in water, we just took the graphite oxide and we zapped it with microwave, and then like popcorn, it enormously expands. And this is what it looks like in SEM after that irradiation with microwave. You can get the same thing through thermal shocking by dropping it through a hot oven, for example. And so we published on this material as an electrode material for supercapacitor. But I think perhaps more interesting was we took that material, microwave expanded graphite oxide, and we decorated it with potassium hydroxide. So we took this material and we put it in aqueous KOH at different KOH loading levels in a parametric study. And when you dry it down, you get lots of small KOH particles all over it. And then when you heat that, and that's one industrial scale method of making activated carbons from coconut shell and from wood and so on, you end up typically converting some of the carbon to potassium carbonate and having small channels and holes in the carbon. And I thought it might do something like this, but this is wrong because when we did simple elemental analysis of the product material, we found little evidence for edge atoms. There was very little O in hydrogen. And so unless there were a lot of dangling bonds that were somehow protected, which wasn't the case from ESR, looking at the spin count, it must have been the case that this picture is just wrong. And so somehow, which we still don't know, we need to study more in the future, I think the KOH is knitting edge atoms together, sort of healing the structure in some interesting way. And we end up with atom-thick walls everywhere we look by high-resolution TEM, and also very high specific surface areas and the presence of 7- and 8-membered rings, as well as pentagons. And a good pore distribution for consideration in terms of micropore and mesopore for an electrode material. And so this is Eric Stock's work. He runs the TEM group at Brookhaven, but he went over to the TEAM instrument at Lawrence Berkeley Lab, where he used to work, one of the best aberration-corrected systems in the world, and could find octagons and smaller n-gons as well. And that reminded me of the literature I had seen in the early 1990s on, the theoretical studies of negative curvature carbon. But we're not saying we have negative curvature carbon, certainly not everywhere here, but it at least reminded me of that. And so, briefly, can you have such high surface areas in negative curvature carbons? We just went in to look at what the physicists, the structures they had studied for other reasons, like they looked at electronic structure and so on, but we just had the simple question, what is the specific surface area of some of these negative curvature carbons? And so picking 4 of them that had different densities and different unit cells, we find that the specific surface areas in meters squared per gram varied from around 3,300 down to around 2,800. So it just happens to be a coincidence that the scaling factor is 1,000. If you have a question, I can show you that. So, we can think of this as a very interesting target material for a variety of different reasons, but one being perhaps as the ultimate electrode material for electrical energy storage for supercapacitors and possibly for batteries. If one could just dial in exactly the pore structure that you wanted and have a highly extended network that was very electrically conductive and completely remove the issue of particle-particle resistance and so on. So I'll finish with this, just showing we did get very promising results in terms of energy storage on a gravimetric basis. And then if you compress the material to increase the density, we also, I'm not showing you those results, but we got promising results when you push the density up around 0.7 or 0.8. Here the density is only about 0.3. So on a volumetric basis, it wouldn't be as impressive. I'll finish by just adding one more point, which this is after we published in 2008 an article in Nano Letters where we studied and were the first to report on supercapacitor studies with the exfoliated reduced graphene oxide material. Every single carbon we studied until this one always had better performance in aqueous electrolyte than the organic or the IL electrolytes. And I tentatively think that's because this one is much more carbon pure. Perhaps it's being wet better than by the ILs, but it was quite frustrating in my group time after time after time when they wanted to work with the large electrochemical window IL versus the 1-volt aqueous electrolytes, that the aqueous electrolytes were always significantly better. Okay, so thank you very much for your attention, and I look forward to any questions that you might have.
Thank you very much. It's a very interesting talk, very informative. Nice to see some of the history of carbon materials. Yes, I'm sure there's some questions. We can take a couple.
Thank you very much for very interesting and fascinating talk. And I have something to ask. One is that the last part of your talk, you showed how to prepare negative carbon graphene based on graphene oxide. And
Maybe this one.
Yeah. Could you show me how to prepare that one?
Sure, I went through that kind of quickly.
Oh, one more part.
Mm-hmm. Yeah, so Professor Nakayama, first I should be careful. It inspired me to think about negative curvature carbon, but we don't think this is a negative curvature carbon, at least not everywhere. But it is a fascinating material. The way we make it is to start with graphite oxide, and then we irradiate that in a simple microwave oven, and it undergoes this expansion because of the interlamellar water. And then we end up with structures that look like this in SEM. And that has a surface area, roughly around this value. So not like single layer graphene around 2,600. Then we decorate this expanded graphite oxide, we call it microwave expanded graphite oxide, or MeGO, with small KOH particles by soaking it in aqueous KOH and then drying it. And then under different loading levels of the KOH, we then study what happens when we heat that intermediate material that's been decorated with the KOH particles.
What's the role of KOH activation?
Yeah, the KOH in other studies, so we actually looked up the recipe essentially in a textbook about industrial scale processing to make activated carbons. The product material is potassium carbonate. If all the KOH were to react, there would be potassium carbonate and then the activated carbonate. And we have to wash out the potassium carbonate and dry and potentially then do another heat treatment, but at least dry the material so that we can then study its characteristics, like its structure by techniques like TEM, its surface area by gas adsorption, its powder conductivity, and so on. So it's that product material that we call activated MeGO that I'm showing you these high-resolution TEM images of. And I know this doesn't convey it, but Eric Stock called me up from Berkeley, where he had been looking at this material for 4 days, and he says, everywhere I look, it's atom thick. And then we did eels on samples that we could control the thickness of. So eels measurements are questionable if they're done the wrong way. So we had very good advice about that. So we had samples where the thickness was very uniform. And so that TEM eels, as well as high energy resolution XPS by Bob Wallace at Alice, and then later by Yoshitaka Ishii at the University of Illinois Chicago, solid state NMR, without knowing the other labs and what they were getting, they all agreed that it was almost entirely sp2. In fact, at the error limits, no sp3. Can't say there's none. So that indicated that it was sp2 carbon and also atom-thick walls, which agreed with the picture of very high specific surface areas. And so it was a consequence of Eric having found 7 and 8 membered rings and a surface area bigger than graphene that had me reminded of the negative curvature carbon. What has been a little, frankly, frustrating is Eric was very excited about following our work with a detailed structural analysis of a MeGO, but in any TEM, and including his aberration-corrected TEM, the material is moving, it's vibrating a little bit, and so he hasn't been able to sort of do tomography with aberration-corrected TEM to map out detailed structures the way he wanted to. He's now got this fancy new camera that can take, I think it's at least tens of thousands of images per second, where each image still has the signal to noise or close to it that the present day systems do over a second acquisition. And he's hoping that on that time scale it won't be vibrating too much, but that those studies are underway. Otherwise, getting the detailed structure via TEM might be very tough for this.
I think the product should be a material containing many different kinds of superstructures. So my question is, how do you control such superstructure?
We don't. In this, we're not claiming. This was a surprising. Yeah, this was just a surprising result to us, where we didn't know we would get those sorts of specific surface areas. We didn't know we would get such an appealing distribution of micropore and mesopore. I don't proclaim to be any sort of expert on supercapacitor, but there are people like Patrice Simon in France who have studied them for his whole life. And when he saw this, he immediately wanted to try some of his electrolytes because that's a very unusual distribution of carbon of such high specific surfaces.
So at this moment, no way to control this size superstructure.
I would say that's a great question, and that's why we're very interested in these sorts of structures. Like, could we challenge our chemists and that they could actually make them. It's a grand challenge for our center to do that. It's one way or another. Yeah.
Thank you. We'll be time for one more question. Prof?
So I'm very interested to see the use of the graphene as kind of this corrosion inhibitor on some of the metal quartz. And you showed a lot with copper.
Yeah.
And I think a copper nickel alloy. So I kind of a couple questions. And you were growing it using CVD.
Right.
Several questions I could have are, other materials, other metals, different processes to grow besides CVD. Are those available? And what about the mechanical integrity?
Right.
Like scratch resistance.
Oh, those are great questions. Yeah, so I think that these ultra-thin films may not be useful for abrasion applications where abrasion is present. There are a lot of other exciting applications where you don't have abrasion, like giant vessels that hold certain liquids and things like that. So that's a very important point. Now, at some thickness, or if one thinks of ultimately perhaps we'll have these sorts of coatings like the diamane, they might be much more scratch resistant and resilient in terms of abrasion and scratches. In terms of sort of the integrity, I think research is needed. There was an interesting article published from Alex Zettel's group at Berkeley where the title was kind of catchy. I don't remember it exactly, but it was basically graphene is the worst corrosion coating. and although they didn't explicitly say it in their article, there is a reason why that could be, and why hexagonal boron nitride might be a much better choice, or the diamane or something like that, where you have an electrically insulating film. Because if you look under galvanic corrosion, just on Google, you find some nice diagrams that show graphite is the most noble material. So, it's more than any other metal, like even gold, for example, and so it will behave like the cathode. So if you have a pinhole, then you have an electrochemical cell set up if there's water present between the graphene and let's say the substrate. That could drive corrosion much faster than if the graphene wasn't even there. Yeah, so my easy solution to the Zettel group paper is simply use multi-layer, and make sure there's no pinholes. It doesn't have to be monolayer. There's nothing sacred about monolayer. It's just interesting that even a monolayer can protect. And the other thing is as we get better and better material, hopefully eventually graphene will just be like plastic foil and will be perfect single crystal for kilometers in length, and then no grain boundaries or defects, and so on. So, that's where I think the excitement lies. And then realizing that, maybe in terms of this galvanic cell issue, it might be other materials might be better. And in terms of the scalability, the flake material, would be significantly better also currently anyway. And so it's open questions about can that be found to be really durable and work over very long periods. But I think if it were graphene platelets, we know when we make reduced graphene oxide, we get a distribution from XRP that's fairly broad in terms of interlayer spacing, like a paper-like material from the RGO. But the interlayer spacing is roughly around 3.7. So there's not water in there, and it is repelling water in a sense. It's hydrophobic, and so I think there would be a reasonable chance that could be a successful coating. Yeah, I think that this is an area where I haven't seen many studies, so it looks pretty wide open. We'd be very happy to collaborate potentially with others in this, just because we have to watch our bandwidth. To me, this is a very exciting area, and there's a lot of really interesting fundamental science, but we just happen to be also trying to make these pure carbon structures and so on. Yeah.
Okay, and I'd just like to ask, we've got quite a young crowd in today, and a lot of the researchers in I2CNER are kind of students or mid-level career. You've had quite an exciting career, and been all over the place. Do you have advice for the younger scientists of this generation?
Oh, that's a very interesting question. I think my advice is, sort of always the same, which is have fun, make nice friends, so you have friends to share, talk with, and then if you don't feel passionate and not something else bothering you in life, then maybe it's not for you. Hopefully you're quite passionate about it as well. I think those are among the main things. I mean, I can give you a quote from Albert Einstein that I like, but of course it was in German, but translated it was, I have little respect for that type of scientist who's always drilling through the thinnest part of the wood. So it's valuable to take on very challenging projects. Not that every single project has to be home run, because sometimes it's very important to make incremental progress, but understand something better and better and better also. So I see how that has helped my group and how it has hurt my group. And I don't want to say my group, but I was very excited about getting away from methane. But we had everyone very interested in methane and what are all the detailed mechanisms, and so that was very valuable to burrow deeper and deeper and deeper with methane. But we missed many exciting opportunities with other ways of making graphene with other sorts of hydrocarbons. Now we have a chance to come back to those issues, and there will be, I think, many exciting avenues where we won't have exactly graphene per se, like this recent paper from Virginia Commonwealth University, Perigena, but also, I think importantly, in collaboration with some Chinese colleagues. And I think the theoretician's wife saw this beautiful tiling with just pentagons from Egypt in an artwork. And apparently this is in sidewalks and stuff. I've never been to Egypt. And they thought, well, carbon and only pentagons, what does that lead to? Actually, it's a fairly high energy carbon, so it might be quite difficult to, if made, it might not be so stable. But that's an example of, wow, I mean, that's been there, but no one ever thought to look at that and realize that maps to what's going on there. So I think also trying to be, on the one hand, you want to do really good science and be very careful with your science. On the other hand, very adventurous and think about, well, what are we just missing here? What could be completely different? An example is Professor Belowski, I think, has that capability. And so we have a challenge now where we're trying to hydrogenate multi-layer graphenes in new ways. And how do we know how much hydrogen is actually on the surface? How are we going to know that? And so he just said, how about we tritiate it? Tritium is not so easy to work with, but then there's problems with this. It may not work, but even fundamentally it might not work. But that's just the type of thing we just think way outside the box. In principle, you could tritiate it. In principle, you could count the number of tritiums very accurately and so on. So just think unconventionally is useful.
Okay, thank you very much. On behalf of I2CNER and Kyushu University, thank you very much for a really nice talk.
Oh, thank you.